So I was mentioning in the intro to energy chapter, we mentioned work. A lot of times we associate work with a job or something like that, but we want to look at mechanical work here. So if energy is the ability to do work, then work is equal to the change in energy. So now energy, just a side note, energy is a scalar. So it doesn't matter what direction you're going, but work is going to be a vector. You're going to see that it's going to have a vector kind of connotation, and it depends on what direction things are going. So you're not going to have it. It's not going to be like a true vector, but you'll see you have plus and minuses. We'll have to worry about those plus and minuses. So again, it's not a true vector like force and acceleration per se, but we'll have to kind of worry about, is that work, are you gaining energy or are you losing energy? So for example, if you're slowing down, you're having a negative work. So for example, work is equal to change in kinetic energy. It's kinetic energy final minus kinetic energy initial. So if I'm slowing down, I have negative work being done on my car. Okay, so that's how you want to kind of look at it. It's not a vector per se, but it does matter if it's positive or negative. So when you're doing the homework online, just kind of make a mental note that you have to worry about positives and negatives. So I'm going to look at a table here, the book on it, and if I push down on the book, that book is not moving. Okay, so there's going to be no motion here. But let's say I apply this red force in that direction, or maybe even this direction. So I would actually be able to get the book to move toward the right. Okay. Now the force A versus force B, A is going to be better to get it to move to the right as opposed to B, and then force C is just pointless. Force C is just not going to move the book at all, except for maybe through the table if I break the table. So this leads to one of the other equations we use for work. Work is going to equal what I call force parallel times the distance moved. So a lot of books do this. They do force times cosine of theta times d. You got to be careful because it depends on where that angle is that's given. So you want to look at the force. You want the force along the motion, and d is going to be the distance traveled or the distance moved. Okay, so kind of be careful with this equation. I know a lot of textbooks give it, but that theta is dependent on whether it's going to be cosine or sine, where that angle is given. So in reality, you're wanting to use the force that's along the motion and then the distance that's being moved. So just kind of keep that in mind. So now work, let's look at units again. If work is equal to change in energy, that means it's joules. But if it also equals force times distance, that's a Newton meter. So you can write it in either way. Work can be Newton meter, work can be joules. Both are acceptable and very much appropriate. Now, for those of you that do CrossFit or exercising, there's a lot of discussions about which type of exercise is good. Is there a lot of work, a little bit of work over a long period of time, or a lot of work over a short period of time? And that kind of leads into our power discussion. Power is equal to the change in work over the change in time. Okay, the amount of work that's done over a given amount of time. Like CrossFit, for example, does a lot of work over short spurts. So again, a lot of you are going to physical therapy or exercise science or something like that. So power is part of the discussion about in health and exercises. And again, we've got to remember every person's different, so everybody reacts differently. When we're looking at power, we're looking at work over time. Now, that means unit-wise, work is joules per second, But a lot of times, let's jump to second semester physics. A lot of time when you say power, and I'm talking about light bulbs, we're talking about watts. A 60-watt light bulb is how powerful that light bulb is. 100 watts, so forth. So this joules per second actually equals a watt. Now, if you notice for work in watts, I wrote the words out because we already have weight as W. We have so many things going on. So we have a lot of crazy equations going on. But so here's your introduction for work and energy. Again, work is equal to the change in energy that's being done. Again, energy is conserved, so you're looking at a specific type of energy, whether it's gravitational potential or kinetic or something like that. But you also we're looking at force, an object that's moving over a distance, how much force is being required to move that. And again, if I come back to this picture with the table, see my muscles will eventually get sore. I'm doing chemical potential energy. I'm applying it in my muscles. My muscles are doing work, but I'm not doing any mechanical work. When you study, your neurons in your brain are doing lots of work and you get tired, but you're not doing any mechanical work. So in this part of the chapters, this part of Physics 1111, we're dealing with mechanical work where we're actually moving something from one position to another.